Hello everyone, and welcome back to the last question we'll be doing in the 2013 midterm, which is question 3. And the reason why it's the last question is because force reduction, especially distributed loads, which is typically seen as question number 4 in midterms, will not be on the exam this year, so we don't have to really worry about it. If you're doing it and you're studying it really hard, well, that's great. It may help you a bit for the second half of the course, but for the midterm, it won't benefit you. So if you're doing it, I recommend stopping, because we're going to get into something which I consider a real treat. And that is question 3 of 2013 midterm. And this is the question that most students are driven crazy by. And it includes me, because this was actually my midterm question when I took Eng 130. And I remember it clear as day. I remember going back to Lister and swearing about it after. This one sucks. And sure enough, as fate would have it, I have to relive it every year when all the students always ask me, well, what do you do for this question? What do you do for this question? So it's kind of a relief that I know that I'm going to do it once more, a nice video, and I'll never ever have to try and solve it again. I'll just say, look at the video. I don't want to go into it, because this question is so bad, but so good at the same time. And it's so good because it uses absolutely everything you guys have learned from the second you guys came here to this point right now. It's really a masterpiece of a question, but it's just terrible at the same time trying to solve it. But we're going to go through it, and hopefully this will be the last time I have to solve it. So the thing that sucks about it right from the beginning, a lot of words. So let's just go through it, try and figure out what it's asking, stuff like that, and we'll go from there. So homogeneous square plate with a total weight, so total weight sounds important, of 4 kilonewtons, is supported by the 4 cables shown in figure 3. These 4 cables are connected to a spring Fe. Okay, well, it has a spring. That sucks. And that's at point E. If the magnitude of the moment, oh great, so we came with springs and now we got moments, created by the tension in cable AE, so tension in cable AE, around the point F, so this is important because we need a point for moments, is this. Calculate the unstretched length of the spring. So in the end, the question's kind of simple. It just wants the unstretched length of the spring. How do we find that? Well, we're going to have to figure that out. So what the question also says is O is located at the geometric center of the plate. The coordinates for point E, so point E is 0.001 meters. Neglect the thickness of the plate as well as the weights of the cables in the spring. Also neglect the elongation in the cables. So it gives you a hint too. I'm not going to read the hint because I'm just going to discuss it with you guys because it's actually a very important hint. But what do we do? Where do we begin? So what I like to do in these type of questions is I'm just going to look at what it wants. And this question is very nice in the sense that it's just asking for one thing. Just one simple answer, and that is the unstretched length of a spring. Okay, well, let's think about that for a second. And we have to just kind of take it one step at a time. Unstretched length of the spring. Well, in all of the formulas that you guys have, there's only one formula that has the unstretched length of the spring inside of it. And that is to do with the force in the spring. So we know the force in the spring is going to be equal to its spring constant K, and it's going to be the length of the spring minus the unstretched length of the spring. Okay, well, that formula doesn't look so bad. And in the end, it wants the unstretched length. So right here, this L naught, this is what we want. So I'm going to put what we want. What we want. A lot of W's there. Okay, so it's as simple as finding the other 3 remaining parameters. So let's go through real quick and see, maybe just from the question, if we can get some. So the first one we'll check is K. Well, if we look right on the picture, it says K is equal to 10 kilonewtons per meter. So K is equal to 10 kilonewtons per meter. Okay, well that was easy. What about the force in the spring? Well, it's not exactly as obvious as K, but let's think about this just from a mechanics based. That spring is holding up the entire plate. The entire plate. So if the entire weight of the plate is 4 kilonewtons, we must know that that force in the spring is actually going to be 4 kilonewtons because it's holding up that entire plate. The spring acts alone. Okay, well, this is actually getting really easy. We need 3 parameters, and we already have 2 without basically doing any work. So now we have to look at the stretched length of the spring. So we want the unstretched. What's the stretched one? And this is equal to, and this is when you guys go, oh, because we're not given it. We don't know what it is. We're going to have to find it somehow. So the stretched length of the spring, that is kind of the whole trick to this question. So let's try and figure out what other information we're given. Well, kind of the big piece is we're given a moment. It says the moment created by the tension in cable AE around point F is 2√2 kilonewton per meter. Okay, well, how does that help us? Now let's just write it down. Let's just figure out. So what it's saying is the moment around which point? It says point E is equal to position vector. Remember, this has to go from the point to the force. So this has to go from point F to E. Sorry, this isn't the moment about E. It's connected at point E, but the moment is about point F. So I need to erase this real quick. So we're looking at the moment about F. So it needs the position vector that goes from the point to the force, so FE. And we're going to cross this by the force vector. And it says in the question, the force vector AE. And we know that since it's in tension, it's going to go from E to A. Okay, well, how does this help? And this right here is what's going to give it away. This right here, this position vector FE. Because remember that a position vector, the position vector RFE, well, that's going to be the coordinates of E minus the coordinates of F. Okay, well, we're actually given the coordinates of E. It says it's 0, 0, 1. So then we're going to minus the coordinates of F, and then, okay, well, we don't know what F is. But this is why it's so interesting, and I'm going to do this in the pink color. Coordinates of E, we know is 0, 0, 1. Coordinates of F, well, we know that it's right above the origin, so the first two are going to be 0. And then the next coordinate, well, we don't know. We don't know. So for this coordinate, let's just put alpha, because we don't know what it is. And these are going to be units of meters. But this is what's interesting, is if we know that point E is 1 meter from O, and let's say that we know what alpha is, and we know that it's alpha meters from point O, we can find the distance between these 2 points right here. Because this distance is going to be alpha minus 1. And that distance right there, if you guys look, that's actually the stretch length of the spring. So that's why this is so important with the moment, is because from that position vector, we can determine the stretch length of that spring. So if we were to do alpha as kind of our unknown, we're going to go minus 0, 0, oops, not 1. 1 is already there. This is going to be alpha. So our position vector that we're going to have to use in our cross product is going to be 0i plus 0j plus, and I'm going to go in brackets, 1 minus alpha, and that's in the K. And this will be units of meters. Where this, and I'm going to put this in pink, this 1 minus alpha, that's going to be the L of the spring, which is what we want to find. And it makes sense, because if we look at this formula, the force in the cable, well, we don't know it yet, but we can find it. The moments around F, well, we don't know that, but we know the magnitude of the moments around F. So if we can find those two, we can solve for L. And if we look up here, if we know L, we can solve for L naught. So that's kind of the general way this question has to go. But now it becomes a real kind of pain in the ass doing that cross product. And because the first thing that we're going to need is we're going to need FEA. FEA. Because right here, if I'm going to do it in a different color, let's try red. FEA goes from here all the way down to here. So now we're going to need FEA, and the thing about the cross product too, it has to be in Cartesian vector notation. So we're going to need to try and find a unit vector. That's kind of the hint towards it. We're going to need to find a unit vector. Well, that shouldn't be too bad because we know a bunch of the coordinate points. So this is going to be equal to the magnitude of FEA times the unit vector of EA. And we're going to run into a problem later because if you guys want to think ahead, what is the magnitude of FEA? Well, we don't know. So it's going to be interesting. So let's just leave that for now, and let's focus on UEA. Because we know that's going to be the position vector REA divided by the magnitude of REA. And we can find the magnitude if we know the vector itself. So what we can do is we can go REA is going to be equal to the position vector at A minus position vector at E. Okay, well, not too bad. So let's look. Point A, right over here, we know it's going to be 2, -2, and 0. Because it goes 2 in the x direction, -2 in the y direction, and it's in the xy plane. So we're going to go equal 2, -2, and 0, minus, and we know that the coordinates of E are 0, 0, and 1. So this position vector is going to be 2i minus 2j minus 1k. And that'll have units of meters. Now, we can also find the magnitude of this position vector. So the magnitude of REA by just taking all those components like this and squaring them. So we're going to have 2 squared plus 2 squared plus 1 squared, which is equal to, it's equal to square root of 9, but the square root of 9 is 3, so we're just going to put 3 meters. So I'm going to finish this off, 3 meters. So now that we know that the unit vector EA is going to be equal to, in brackets, and I'm just going to divide all those components by 3, nice and easy. So we're going to have 2 over 3i minus 2 over 3 in the j plus 1 over 3 in the k. And again, it's going to have no units. All right, so now if we look up at our force formula, it's actually very, very nice because we got UEA, we're trying to find FEA, but wait a second. We don't know the magnitude of FEA. So now we're going to have to look up and we're going to say, okay, well, does the question give us anything to help us find it? And that's when we look at the hint. And it says a homogeneous plate implies that the center of gravity for the plate is at the geometric center O. This means that the magnitude of the z component of the tension in cable AE is W over 4 due to symmetry. And it makes sense because what it means by symmetry is each of those cables should be carrying the same amount of force. So the z component is going to be W over 4. So if I were to look at this and go FEA in the z component, we know that's going to be equal, W over 4, which is equal to the 4 kilonewtons divided by 4, which is equal to 1 kilonewton. So the z component for all those forces should be 1 kilonewton. Now, this is when we're going to have to look back up at this equation and figure it out. Because using this equation, which I'll kind of highlight in pink, we can conclude this with it. Because this is for all 3 of the components. But what we can say is that FEA, I was just going to put a lowercase e, FEA, comma Z, is equal to the magnitude of FEA and this one shouldn't have a hat because it's just the Z component, times U EA comma Z. So therefore, FEAZ, well, we know that that's going to be 1 kilonewton. And it's going to be times the magnitude of FEA times the Z component of the unit vector, which we know is 1/3. So from there, what we can do is we can just move the 1/3 to the other side. We know that FEA, or the magnitude of it, however, is equal to 3 kilonewtons. So from there, we can go back up to the equation with the pink arrow, and now we know FEA, we know that UEA, we can then find FEA in Cartesian vector notation, which is going to be just multiply the 3 into the unit vector, and since it's all divided by 3, it actually works out very simple. It's going to be 2i minus 2j plus 1k. And this will have units of kilonewtons. So now we found FEA, and if we go back up to our moments about F is RFE, which has our unknown in it, but it's still kind of solved for it, and times FEA, which we now know. So if I were to do the moment about F, again, this is going to be the cross product. I can start drawing in my nice matrix. So we know that the top row, I, J, K, always. The second row is going to be the position vector, which we have as 0, 0, and then 1 minus alpha. So 0, 0, 1 minus alpha. And then at the very bottom here, we have our force vector, which we now know is 2, -2, and 1. So perfect. Now, what we can do is whatever method you guys like. I know different professors do different methods. It doesn't really matter which one you pick, because you should get it right in the end. I'm going to do the fish method, but I'm not going to go through the calculations. I did that last example. If you have questions about the calculations, it's very easy to just go back and look at it. So what I'm going to get is this is equal to, and this is the trick, is this should be a vector. Remember, cross product gives you a vector. So even though our relation to the moment at the very top of the question is a scalar, we're not quite there yet. So that's the magnitude of the moment, but to find the magnitude, we need the vector. So looking at the I component, it's going to be 0 times 1 minus, and in bracket 1 minus alpha times -2. And this is in the I direction. And we go minus, so remember the J component is the only one that's going to have that minus to start it. And it's going to be 0 times 1 again, minus 1 minus alpha times 2. And I can end that with the J. And then I can go plus, and this is going to be the last one, and it's going to be 0 times -2. Minus 0 times 2. It's in the K direction, and that's the end of the vector, so we can put the squiggle brackets in, and it's going to have units of kilonewtons times meters. So this is pretty ugly, so what I recommend now is just tidying it up. So we know that the moment here about F as a vector, so remember, still in a vector, we're not in magnitude yet, is going to be 2 minus 2 alpha, sorry. 2 minus 2 alpha in the I direction, plus 2 minus 2 alpha, and that one's in the J direction, plus 0 in the K direction. And this will have units of the kilonewton meters. All right, so that's a little bit better, but we're not quite what we're there for. So remember, we don't have the Cartesian vector notation of MF. What we have is the magnitude of MF. And the question says that this is equal to 2 root 2. Okay, well now the question becomes, how do we find the magnitude? And it's nice because the magnitude for vectors is always the same. Always. It's the same formula where we square all the components, add them together, and then square root that. So, if I do that for this case, what I'm going to get is the square root of, and it's going to be 2 minus 2 alpha squared plus 2 minus 2 alpha squared, and then plus 0 squared. That line was so bad. And we remember that this is all equal to 2 root, oops, I don't know what the heck happened there. 2 root 2. Okay, so now we're kind of getting somewhere. Because now we have one equation with one unknown. And that's exactly kind of what we're looking for. One equation, one unknown, nice and easy. Now, the problem with this is it becomes really hard to solve. Really hard to solve. So what I'm going to do here is instead of 2 root 2, I'm going to put equals root 8. So now, I can just take the stuff that's underneath the brackets, underneath the root, and equal it to the stuff underneath the root on the other side. So therefore, right here, I can go 2 minus 2 alpha squared plus 2 minus 2 alpha squared is equal to 8. Okay, not bad. So if I have 2 minus 2 alpha squared plus 2 minus 2 alpha squared, well, that's just 2 times 2 minus 2 alpha squared. And that's still equal to 8. Okay, well, still kind of getting somewhere. Next thing I want to do is let's divide both sides by 2. So let's divide by 2, divide by 2. So now we have, oh, I'm just going to erase this or else it's going to get confusing. So what you guys know what I did? I just divided both sides by 2 to get rid of it. So what I have now is 2 minus 2 alpha, and this is squared still, it's equal to 4. Okay, so still on the right track, things are getting easy. So now we got to get rid of the squared. We're squaring, we got to square root both sides. So 2 minus 2 alpha, so we just got rid of the square, is equal to, and then the square root of 4, well, that's 2. Now, this is the most important part of this question, and this will mess up a lot of students, and I'll admit it messed me up. When I was an undergrad, the beginning of this question messed me up when I was an undergrad. I couldn't get anywhere in it. But this messed me up now is, remember in math, when you square root something, it actually has 2 values, plus or minus 2. And we're going to see why that's so important right now. So let's pretend that we have plus 2. Okay? So what happens is we have 2 minus 2 alpha is equal to 2. Okay, so if we do that, we're going to solve, and we're going to get alpha is equal to 0. Okay, well, that's a problem. Because remember, the alpha should be higher than 1. If it's less than 1, in this case it says it's 0, what it's saying is that point F is actually down on the plate, which is impossible. We know that point F must be above point E. So we can right away tell if we guess alpha is plus 2, answer doesn't make sense. So I'm just going to put here, not possible. All right, so hopefully the next answer is possible. So if we go minus 2, we got 2 minus 2 alpha is equal to minus 2. And when we solve that, we get alpha is equal to 2. And we look up at the very top, 2 is greater than the 1, so therefore, yes, this works out fine. So this is good. So we're just going to put good. And now that we know alpha, remember that L naught, or sorry, not L naught, but L is equal to 1 minus alpha. And this should be the absolute value, because remember that this is going downwards because we're going from the distance from, oh, how do I describe this nicely? It's because we're going downwards. So this is, the best way to describe it is actually this. Don't listen to my shenanigans for a second. We can now find the position vector. So the position vector R that goes from F to E, FE is equal to 0I plus 0J, and then we had the plus 1 minus alpha. So plus 1 minus alpha is actually negative 1. So we're going to go negative 1, and that's in the K direction. That meters. So the reason why it's negative 1 is because we're going from point F down to point E. But the best way to put it is L is equal to the magnitude of our FE, which is going to be equal to the square root of 1 squared, which is equal to 1 meter. So, you see how this question looks so complicated, but in the end, the stretch length is just 1 meter. It's kind of a dick move, if I'm being honest, but it's so funny because this question has caused me so many problems, and now it's it's still rubbing it all into my face. So now we found L, and it was a very, very tricky way to find L. That's why this question is brilliant, because this is the best question you can ever have. All right, so now, quick summary. You know, the force in the spring is equal to K, L minus L naught. Well, now we can substitute values because we know that the force in the spring is equal to 4 kilonewtons. The spring constant is 10. L is 1, and minus L naught, which is what we're searching for. So if we move 10 to the other side, we're going to get 0.4 is equal to 1 minus L naught. So therefore, L naught must be equal to 0.6 meters. So this question, absolute nightmare. The answer, so simple. And it's one of those questions that, this is why I have a lot of troubles when students ask me, well, what will be the kind of the concept of each question? Who knows? Some professors, like I got to give this professor whoever made this credit, because this involves every single thing you could imagine. So if you get something like this, I'm sorry. It's a hard question, but you just got to remember all the fundamentals. So again, what I did, I looked for, okay, well, what's the unstretched length? What's the formula for that? Fs, K, L, L naught. Well, Fs and K were given. Well, how do I find L? Well, that's actually going to be the magnitude of the position vector Fe. Well, okay, how do I find that? Well, I can find the moments with the force vector Ea, and we're given the magnitude of that moment, so we can kind of work backwards to find L. And that's what we did. And then the math thing right here at the end, just a nice trick. But then we can find L, go back to our original equation. We find L naught is equal to 0.6. So that was one heck of a problem. I hope you guys understood it. It's hopefully the last time I'll ever have to do it, because I do not like this problem at all. But yes, so thank you guys all for listening, and best of luck on your midterms. I know all of you will do great. All right, thanks guys. Good luck.